The date was August 2nd, 2009. Cassini was completing its 61st targeted flyby of Enceladus. By then, the moon's south polar plumes were old news, a stunning, solved mystery. Brilliant jets of water ice erupting from tectonic fractures called tiger stripes, fueled by tidal heating from Saturn's gravity. A textbook perfect example of cryovolcanism. The press kits called it the most promising habitat for life beyond Earth. We'd found simple organic molecules in the spray methane, propane, the basics. It was exciting, but safe. It fit our models. On this pass, the spacecraft was tasked with a deep dive through the densest part of the plume. Its cosmic dust analyzer, CDA humming, ready to catalog the size and composition of icy particles. I was in the dedicated CDA lab at JPL, the graveyard shift, monitoring the real-time telemetry with Myra. The data stream scrolled down our screens, a predictable rhythm of water ice signatures, the occasional blip of sodium chloride sea salt, a tantalizing hint of a subsurface ocean, not with a bang, but with a stutter. The CDA's higher rate mass spectrometer captured a cluster of particles within a millisecond. The mass-to-charge ratios painted a bizarre profile. Myra leaned forward, her face illuminated by the cool blue light of the monitor. "Alistair," she said, her voice unnaturally calm. "Look at packet 4417. I pulled it up. The graph showed a series of sharp peaks at masses that made no sense for water ice. 56, 68, 94, 112 atomic mass units. There were traces of iron, but bound in a complex carbon-rich matrix. It looked fibrous. Contamination, I said automatically. The first and safest reflex. A fleck of paint from the spacecraft bus. A bit of insulation at 94 AMU. Myra's fingers flew across the keyboard, calling up the particle's velocity and trajectory data. It entered the spectrometer at 4.2 kilometers per second. Relative, it came from Enceladus, Alistair, not from us. And look at the ancillary data. The impact ionization pattern. I looked. When a particle strikes the CDA's rhodium target, it vaporizes and ionizes. The pattern of that ionization tells you about the particle's structure. A pure water ice grain gives a clean Gaussian burst. This was a ragged, sustained signal, as if the particle hadn't just vaporized, but had unraveled. "It's got a microstructure," Mira whispered, "a complex one." We ran diagnostics. We cross-referenced with the spacecraft's attitude control system, checking for thruster firings. We looked for solar flares that could cause instrument noise. Everything was nominal, except for packet 4/17. We filed a preliminary anomaly report. The project manager, a brilliant engineer named Frank, reviewed it. "Interesting," he said, in the tone that meant, "Please don't waste my time." One particle, a cosmic dust grain, probably interstellar in origin, just happened to be in the plume. Flag it and move on. We should have. But Mira had that look, the one that saw ghosts. She spent her offras writing a filtering algorithm, teaching the software to look for similar ionization patterns in the back catalog of CDA data from previous Enceladus flybys. 3 days later, she walked into my office, her face pale. She didn't say a word. She just placed a single sheet of paper on my desk. It was a graph. The x-axis was time spanning 5 flybys over 3 years. The y-axis was a metric she'd invented, structural complexity index. It was a measure of that ragged ionization signal. 5 tiny, almost invisible blips. 1 from 2005, 2 from 2008, hours from 2009, and 1, faint but undeniable, from a flyby just 2 months prior that we'd missed. They were clustered, not randomly, in time, but correlated with something else. I pulled up the orbital mechanics. My coffee went cold. Every anomalous particle detection occurred when Cassini flew through a specific region of the plume. Not the densest part, but a diffuse, peripheral fringe, emanating from a single, specific tiger stripe, a fracture weed, named Damascus sulcus. It's coming from one source, Myra said. One crack, and it's not constant, it's episodic. The implications were uncomfortable. We weren't looking at simple geochemistry anymore. Geochemistry is messy, stochastic. This was punctual, specific. It had an address. We requested an unscheduled data review with the senior science team. We presented our one particle and Myra's graph. The reaction was a masterclass in academic skepticism. Statistical noise, said the head of the Particles and Fields group. Instrument artifact. The CDA is 15 years old. For God's sake, said the systems engineer. Even if it's real, it's just a complex polymer tholins. We see them on Titan. Space makes weird chemistry, concluded the head of the mission. Only one person didn't speak. Dr. Elara Voss, the team's microbiologist, a woman who'd spent her career studying extremophiles in Antarctic subglacial lakes. She stared at the ionization pattern printout, turning it slowly in her hands. After the meeting, she cornered us in the hallway. "You've ruled out contamination?" she asked, her voice low. "As best we can," I said. "And the velocity data is solid. It's native to Enceladus. The vector is consistent with an origin at Damascus sulcus." "Yes," she nodded slowly. "The pattern. It's not diagnostic, but it is suggestive. It reminds me of the ionization trace of certain long polymers with helical substructures, like certain polysaccharides, a sugar. A complex sugar." My mouth was dry. "Biological, I didn't say that," she said sharply. I said, "The pattern is reminiscent. Biology is one way to make such a molecule. Prebiotic chemistry is another." But she hesitated, choosing her words like a soldier crossing a minefield. "But if you wanted to design an experiment to look for biosignatures, you wouldn't look for a single molecule. You'd look for a pattern of many molecules, in ratios that defy equilibrium chemistry. You'd look for an excess, a metabolic fingerprint." She left us standing there. Mira and I looked at each other. We had no mandate to hunt for metabolic fingerprints. We were dust physicists, but the hook was set. We became conspirators. In the quiet hours, we wrote new algorithms. We begged for time on the mission's spectral archive. We weren't looking for life. We told ourselves we were looking for complexity, a new kind of chemistry. The breakthrough came from a different instrument entirely, the ion and neutral mass spectrometer in BESS. Its job was to sniff the thin gas of the plumes. It had detected molecular hydrogen before H2H was exciting because, on Earth, hydrogen is a telltale sign of water reacting with rocks in hydrothermal systems. It's a potential food source for microbes. Myra had the idea to cross-correlate the NMS hydrogen data with our anomalous particle events. The software churned for a night. The result was a single, stunning plot. every time our CDA picked up a whisper particle. The InMES recorded a simultaneous, sharp dip in the local molecular hydrogen concentration. It wasn't much, a 3 to 4% decrease against the background plume, but it was consistent, as if something at Damascus sulcus was, for a brief moment, consuming the hydrogen, scrubbing it from the EJECTA. Frank called us into his office. He had the plot on his screen. His usual avuncular demeanor was gone. "Explain this," he said. "Not a question, but a command." "We can't," I admitted. "Yet, but the correlation is statistically significant. Something at that location is interacting with the plume chemistry in a non-passive way. It's not just spraying out material. It's altering the material as it comes out. Altering it, how? We don't know. A catalytic reaction on the vent walls, a filtering process." Frank leaned back, rubbing his temples. "You realize what you're implying? You're implying something dynamic down there, something that modulates its environment. It could be a purely chemical cycle," Mira offered, ever the cautious one. "Could it?" Frank looked at her. "Chen, you're the one who found the pattern. Do you believe it's just chemistry?" Mira was silent for a long time. "No," she said finally, the word hanging in the air like a verdict. "I don't. The timing is too precise. The localization is too exact. It looks behavioral." The word behavioral changed everything. Geology is not behavioral. Chemistry is not behavioral. Biology is. Frank stood up and walked to his window, looking out at the California night. "We have flyby 121 in 6 weeks. A close one, 48 kilometers over the South Pole. We were going to focus on Baghdad sulcus. I'm retasking it. Primary objective, Damascus. I want every instrument pointed at that damn crack. InMES, CDA, UVIS, VIMS, the cameras. I want to see its tonsils." But he turned back to us, his expression grave. "This stays in this room. No preliminary data releases, no leaks to the press. We go dark on this. We gather the evidence, we analyze it as a team, and then we decide what it means. Is that clear?" It was the beginning of the secret mission within the mission. We had 6 weeks to plan, 6 weeks to let the terrifying, thrilling possibility grow in the dark. I started dreaming of Enceladus, not as a scientific subject, but as a place. In my dreams, I stood on the icy plain, the great arc of Saturn hanging in the black sky. The ground under my feet was not still. It throbbed with a slow, deep rhythm. And from the dark line of Damascus sulcus, a few hundred meters away, I heard not the roar of a geyser, but a sound like a vast, slow breath, an inhalation, then a sighing exhalation of glittering frost. I'd wake up with my heart pounding, the echo of that sound in my ears. It was just stress, of course, the subconscious processing of data. But it felt like a warning. The flyby, October 15th, 2009, the control room was tense. A different kind of tension from the usual flyby. It was quieter, fewer people, only the essential instrument teams and senior staff. The usual back-channel chatter was absent. We were all watching our own screens, but we were connected by a shared, unspoken dread. Cassini was on Autopno, its sequence of observations locked in weeks ago. We were just passengers. Now InMES is active and nominal. CDA is armed. VIM is acquiring. The calls came in, sterile and professional. On the main screen, a navigation camera image, updated every few seconds. Enceladus grew from a bright crescent to a scarred, complex landscape. The tiger stripes came into view, deep, parallel gouges in the ice, glowing with a faint inner light from the heat below. Damascus was the central one, the widest. Its walls sheared off into terrifying cliffs of blue ice. Closest approach in 10 seconds. I held my breath. This was it. We were screaming over the surface at 8 kilometers per second. All the data was being recorded, stored on solid-state buffers. We wouldn't see it in real time. Mark, Cop, the flyby was over. Now, the agonizing wait for the data downlink. The spacecraft had to reorient its high-gain antenna back to Earth, a process that took 20 minutes. Then the trickle of ones and zeros would begin racing across 1 billion miles of void at the speed of light. The first data to come back was from the Imaging Science Subsystem, ISS. The raw images popped up on screens. They were breathtaking, horrifying. Damascus Sulcus, seen from directly above. It wasn't a clean crack. It was a chaos of collapsed pits, terraces, and ridges. At its center was a series of nearly circular openings, and around the largest vent, the ice was stained, not with a uniform color, but with a pattern, a radiating spiderweb pattern of darker material, fading out into the bright ice. "My God," someone muttered. It looks like no one finished the sentence. It looked like something had seeped out repeatedly from that central pore, staining the ice in concentric rings, a bacterial colony on a petri dish. Then the spectral data from VIMS, the visual and infrared mapping spectrometer, began to auto-process. It mapped the composition of that stain. Water, ice, of course, carbon dioxide. But overlaid on that, in the dark web-like filaments, was a strong absorption feature at 3.4 micrometers. The signature of carbon-hydrogen bonds, organic material, and not a smearit, was concentrated precisely along the dendritic pattern. Ela Voss was at her terminal, her face lit by the spectral maps. "It's not just tholins," she said, her voice trembling slightly. "The CH2-CH3 ratio. It's too high. This is aliphatic, long chains. This is the kind of gunk you get from the breakdown of lipids, or the building of them." The room was utterly silent. We were looking at a fossilized stain of complex organics, arranged in a fractal growth pattern, emanating from a single vent on an icy moon. Then, the InMes data finished its first pass processing. The graph of molecular hydrogen concentration during the flyby appeared on the main screen. It was a smooth curve as we approached. Then, directly over Damascus, it fell off a cliff. A 40% drop, not our previous 3%, 40%. The hydrogen was being annihilated. And as the spacecraft passed beyond the vent, the concentration rebounded, but not fully. It was like something had taken a single deep bite out of the plume. Finally, the piece de resistance, the CDA data mirrors instrument. The log appeared, not one anomalous particle, not 5, hundreds, a storm of them, all clustered in a 10-second window directly over the stained vent. And their mass spectra, they were variations on a theme. The same complex, fibrous signature, but with subtle differences. Different lengths of carbon chain, different minor element iterations. It was a family of molecules. Myra stood up. She didn't say anything. She just pointed at her screen, where her software was rendering a composite of the data. It superimposed the CA particle density map over the ISS image of the stained vent. The particles originated from the exact center of the dark stained web, the epicenter. Frank's voice cut through the silence, sharp and clear. Shut it down. All non-essential downlinks. Preserve buffer integrity. I want a full instrument diagnostic run, now. He was in damage control mode. The data was too hot, too perfect. Frank, I said. We need to process this. We need to understand. We need to not jump to cosmic conclusions. Alistair, he snapped. Then, lowering his voice, this data is incendiary. If it gets out in its raw form, it will be misread, sensationalized. We will be accused of finding life when we have found something we cannot explain. That is all we can. Say we have found an unexplained chemical process of staggering complexity and localization on Enceladus. He was right, of course. Scientifically, he was right. But in our guts, we all felt the paradigm shift. This wasn't just a hydrothermal vent. It was a factory, a highly specific, patterned, cyclic factory that consumed hydrogen and pumped out a suite of complex organic macromolecules. The next 72 hours were a blur of controlled panic. We worked in shifts. The signal was real. At the end of it, we gathered in the main conference room, the senior team, about 15 of us. Frank stood at the head of the table. The findings from E1-1 are classified Level 3, confidential, he began. Level 3 was for data that could cause significant public and scientific disruption if prematurely released. No external discussion, no papers, no presentations. All data is to be kept on the isolated server. We will form a dedicated analysis group. Vance, Chen, Voss, myself, and a few others. Our goal is not to announce, but to understand. We have one overriding question now. He paused, looking at each of us in turn. The weight of the billion-mile journey, the decades of work, hung in the air. We became paranoid. We scrutinized each other's conclusions for bias, for that desperate human need to find a reflection in the void. The strain showed. Mira stopped sleeping, her eyes hollow. I dreamed of the staining, watching it spread in time-lapse, a black lacework slowly consuming a world. It was Mira, in her exhaustion, who found the escape valve. Or perhaps the next piece of the puzzle found her. We're thinking too small, she said one morning, her voice flat with fatigue. We were in the vault, the glow of monitors, our only light. We're staring at the one tree that's on fire. What about the rest of the forest? Frank looked up from a VIMS map. What do you mean? Enceladus is one moon. Saturn has over 86 major icy moons. We have a phenomenon here of staggering implication. We must not assume it is unique. The logic was inescapable. If the process on Enceladus was a fundamental outcome of water rock chemistry under tidal heating, it should exist. Elsewhere, if it was something else, we needed to know if it had spread. Frank authorized a covert review of all Cassini data from Saturn's other large icy moons: Dione, Rhea, Tethys, Mimas, Iapetus. Not a new observation campaign that would raise flags, but a deep forensic dive into archives already in hand. We were to look for anomalies, for whispers. We divided the work. Mira took Dione and Rhea. I took Tethys and Mimas. Alara, with her biological lens, took Iapetus, the bizarre two-toned moon. that had always been an outlier. We were looking for anything: unexplained spectral features, thermal oddities, particle emissions, magnetic perturbations. For weeks, we found nothing but dead rock and clean ice. The silence was a relief and a disappointment. Maybe it was unique, a cosmic fluke, a one-sinisolar system event. Then, on a Tuesday, Elara Voss didn't come to the vault. She sent a one-line email. "I need the full, raw radar scatterometry dataset for Iapetus from all flybys." Now, the Cassini radar was designed to penetrate Titan's haze, but it had been used in scatterometry mode on other moons, bouncing radio waves off the surface to measure texture and composition. Iapetus, with its stark, bright-dark dichotomy, was a prime target. 2 days later, she called us to her terminal. She looked older. "Iapetus," she said, without preamble. "The official story is the dark stuff is lag deposit dust from Phoebe, darkened by solar radiation. The ice sublimates from the warm, dark areas, recondenses on the cold, bright ones. A neat, abiotic feedback loop." She pulled up a standard albedo map of Iapetus. Cassini Regio, the dark hemisphere, was a sprawling blotch of brownish black, like a continent of tar. But the chemistry never quite fit, she continued. The spectral signature of the dark material is too rich, too complex. It has polycyclic aromatic hydrocarbons, cyanide compounds, long-chain aliphatics. It looks processed. She brought up a radar scatterometry map. It measured the radar darkness, how much of the signal was absorbed, not reflected. Over most bright, icy moons, the signal bounced right back. On Iapetus's dark terrain, it was partially absorbed, expected for darker material. "But look at the absorption depth," Elara said, her finger tracing a contour line on the map. "It's not uniform, it's patchy. And here, in this basin," she zoomed in on a large, unnamed impact crater within Cassini Regio. "The absorption is nearly total. The radar signal goes in and doesn't come back. It's a black hole, so it's thicker there," Frank said. "Dust accumulated in a depression, maybe," Elara said. "But then, look at this." She overlaid the radar data with a map from the composite infrared spectrometer. SIRS measured heat. The dark areas absorbing sunlight should be warmer, they were. But in that same radar-absorbing crater, the thermal data showed a cold anomaly. A patch about 50 kilometers across was 10 degrees Kelvin colder than the surrounding dark terrain. "It's dark, so it should be hot, but it's cold," Mira murmured. "That's backwards." "Exactly," Elara said, a fierce light in her eyes. "Unless the darkness isn't just passively absorbing sunlight. Unless it's using it." The room froze. "Using it," I echoed, stupidly. "Endothermically," Elara said. "A chemical reaction that consumes thermal energy." "Heat sink. That crater isn't just covered in dirt. It's covered in a material that is actively cooling itself." The implications unfolded like a nightmare flower. A self-cooling, radar-absorbing, complex organic layer. "You think it's alive?" Frank's voice was a dry whisper. "I think it is metabolically active," Elara corrected. Her scientists discipline a thin wall against the tsunami of meaning. The dark material on Iapetus may not be a lag deposit. It may be a biomass, a sprawling, continent-sized mat that uses sunlight not for photosynthesis, but to drive endothermic carbon fixation reactions. It eats light and gets colder. And over geologic time, it has been consuming the ice, converting it into more of itself. The bright, trailing hemisphere. That's not where ice condenses. That's the refuge, the last untouched ice, because the prevailing dust drift the Phoebe. Dust falls on the leading hemisphere, feeding the thing. It's not a feedback loop. It's a propagation cycle. She brought up one last image, a higher resolution camera shot of the boundary between dark and light. At the pixel level, the edge wasn't smooth. It was fractal, filamentous. Tendrils of dark material reached into the bright ice like roots or mycelia. The silence in the vault was absolute. We had gone looking for another whisper. We had found a scream. Enceladus had a localized geyser-fed factory. Iapetus suggested a global photosynthetic scale infestation. 2 moons, 2 utterly different manifestations. We need to verify this, Frank said, but the command had no force. The data was there. We need a dedicated Iapetus flyby, a low-altitude radar pass over that crater. The next Iapetus opportunity is in 14 months, I said, checking the master sequence. It's not a targeted flyby, it's a distant pass. Then we change the sequence, Frank said, a new grimness setting into his jaw. We have the fuel for one major orbital adjustment. We were saving it for the end of mission grand finale. I'll take it to the director. We'll call it a calibration opportunity for the radar. A unique target. He left to start the bureaucratic machinery. We remained, staring at the fractal edge on the screen. 2 moons, Mira said. One, a deep, hot, hydrogenating vent. The other, a cold, sunnating stain. They're nothing alike, aren't they? Alara countered softly. Both are systems that take in a diffuse, abiotic, energy-sourced tidal heat, or use it to build complex, carbon-based structures with high efficiency. They're different solutions to the same problem, how to persist. One is R-selected, fast, localized, explosive. The other is K-selected, slow, global, patient. The biological terminology was like a key turning in a lock. We weren't just looking at chemistry. We were looking at strategies. The DIVR, CO in getting approval to burn precious hydrazine to divert Cassini for a closer look at Iapetus took 3 months of quiet, intense persuasion. The official story held radar calibration on a unique surface. The real reason was known only to the director, Frank, and our team. The spacecraft's trajectory was tweaked. On November 14, 2010, Cassini would make a pass of Iapetus at an altitude of 1,200 kilometers. Not the closest ever, but close enough for our purposes. The radar would be prime instrument, painting the dark crater with its microwave brush. The wait was agony. We buried ourselves in other work, analyzing the Enceladus factory output, trying to decipher the molecular grammar of the particles. Were they random polymers, or did they have repeating subunits? Sequencing organics from mass spec data is like trying to reconstruct a novel from a pile of letter fragments. But Ilara and a borrowed protein sequencing AI began to see hints of periodicity. Not enough for a code, just a faint rhythm. The day of the Iapetus flyby arrived. The vault was packed now with a few trusted radar and SIRS specialists who'd been read into part of the mystery. We didn't tell them about Enceladus. We just said we had reason to suspect unique chemistry in that crater. Again, the tense silence of a live flyby. The data would be real time, a direct stream. RADAR, scatterometry, is not an image. It's a graph of returned signal strength over time. Radar is active, transmitting. The green wave on the monitor began to scroll, painting the surface as Cassini flew over. Bright terrain zipped by a sharp, higher turn signal. Then, the edge of Cassini Reggio. The signal dropped, but with texture, variations. Entering target region, the radar operator intoned, "We were over the crater." The signal on the screen didn't just drop, it vanished. The line flatlined into the noise floor. "Signal loss," Frank barked. "No, sir, we have lock. We're transmitting at full power. There is zero backscatter, total absorption, total. Better than 99.99%. It's a perfect black body." At radar wavelengths, Alara let out a slow breath. Next to her, the SIR's thermal data streamed in. A map of brightness temperature built on another screen. The crater was a deep blue spot in a sea of reds and oranges, a profound cold spot, just as she'd predicted. "It's not just cold," the SIR's specialist said, bewildered. "It's actively siphoning heat from the subsurface. The thermal gradient is inverted. The surface is colder than the substrate. That's impossible for passive material." Then, the final blow. The radio science subsystem, RS team, who were measuring the Doppler shift on Cassini's signal to map Iapetus's gravity field, raised a hand. "We're getting a microsignature," the lead said. "A tiny, extra Doppler shift localized over the crater, as if the mass down there is fluctuating slightly." "Fluctuating?" I asked. "Oscillating. A periodic density change, minuscule, on the order of a few parts per billion. But it's there. A cycle with a period of about 9.3 hours. 9.3 hours. Not a geological timescale, a metabolic one. A timescale of tides, of diurnal cycles, of biological rhythms." Frank looked at Ilara. Radar-absorbing, mass-oscillating patch of complex organics. She met his gaze. "It's not a stain, Frank. It's a colony, and it's awake." The data was undeniable, and far more dangerous than the Enceladus findings. This wasn't hidden in a vent. This was sprawled across a hemisphere, visible to any telescope that cared to look. We had just never known what we were looking at. The post-flyby meeting was a council of war. The evidence for non-terrestrial metabolic, possibly replicating complexity, was now sitting on 2 moons. The paradigm was shattered. We could not keep this contained. "We have to publish," Elara said. "We have to tell the world." "And say what?" Frank shot back. "That we've found alien life. With this, we have no cells, no DNA, no fossils. We have thermodynamics and weird chemistry. The moment we say life, every skeptic on the planet will tear it apart, and they'll be right too. We need a smoking gun. We need a structure. We need to go back to Enceladus," Myra said, her voice cutting through the argument. She'd been quiet, studying the side-by-side data streams from the 2 moons. Iapetus is the ancient, slow strategy. It's the outcome. Enceladus is the engine, the source, the particles from Damascus, Sulcus. They're not just waste. What if they're the product? What if Enceladus is making the seeds? We all turned to her. "Seeds?" I asked. The atmospheric data was a catalog of prebiotic wonders. UV light from the distant sun cracked methane and nitrogen high in the stratosphere, spawning a zoo of complex hydrocarbons: ethylene, propane, diacetylene, benzene. These coalesced into the Tholin haze that gave Titan its orange pallor and eventually snowed down to the surface. It was a continuous, cosmic-scale Miller-Urey experiment, manufacturing the building blocks of life by the megaton and dumping them on the ground. Yet, when we looked for the next step, for the concentration, the selection, the polymerization of those building blocks into something more, we found nothing. The surface spectra from the visual and infrared mapping spectrometer VIMS showed vast plains of organic gunk. But the signature was generic, a broad, featureless sludge. No sharp absorption lines for complex proteins or nucleic acid analogs. No localized hotspots of advanced chemistry, just a uniform, photochemical tar. It's like a kitchen where someone has smashed all the eggs, flour and sugar together on the floor. Myra observed grimly. All the ingredients are there, but in a useless, mixed-up mess. No cake. Ilara focused on the lakes. If life existed, even a weird, methane-based life, the lakes were the obvious habitat. Liquid solvent, energy gradients, nutrient flow from rivers. Cassini's radar had mapped their shorelines, measured their depths, even caught a glimpse of a mysterious magic island in Ligia Mare that appeared and vanished, likely a transient bubble or floating mass. We requested a deep dive into the radar data from the final close flyby of Titan in April 2017. The radar could measure not just topography, but the dielectric constant of the liquid, a clue to its composition. The methane-ethane mix was as expected. But as the signal penetrated the deeper parts of Kraken Mare, something odd happened. Look at the bottom return echo, the radar specialist, a meticulous man named Ian, pointed out. We were gathered around his terminal in a cramped sublab. In most places, we get a clean reflection off the lakebed water ice. But here, in these deep basins, he highlighted areas on the bathymetric map where depths exceeded 200 meters. The echo is fuzzy, diffuse. It's as if the signal is scattering in a layer above the bedrock. Sediment, I suggested. On a slope this steep, Ian zoomed in. The area was part of a submerged cliff face. Sediment would settle at the base. This is a suspended layer, a cloud about 10 meters thick, hovering 50 meters above the lake floor. And its dielectric properties are strange. Not quite liquid, not quite solid. An emulsion. Droplets of one liquid in another. Or a colloidal suspension. Could it be a bloom? Ilara asked, the word hanging in the air. A microbial bloom. Ian shrugged, a helpless gesture. The radar can't tell a bacterial mat from a cloud of fine clay. But it's an anomaly, a structured anomaly in the deepest, darkest, most stable part of the largest sea. It was a thread, the faintest of threads. We ordered a cross-correlation with data from Cassini's ion and neutral mass spectrometer in MES from its passages through Titan's upper atmosphere. The InMES had sampled the complex high-altitude haze directly. Maybe there were clues in the smallest, most volatile fractions. What we found was not a clue, but a brick wall. Myra was running the analysis. She'd built a model to compare the observed atmospheric composition against a pure photochemical model. What the atmosphere should look like if only sunlight and chemistry were at work. The model matched beautifully, except for one family of molecules, the nitriles, compounds with a carbon-nitrogen triple bond, like hydrogen cyanide, HCN, and cyanocetylene, HC3N. These were crucial prebiotic molecules, the likely precursors to nucleobases like adenine. In Titan's stratosphere. Their concentrations were too low, not everywhere, but in specific, localized layers between 100 and 200 kilometers altitude. The nitrile abundance was 30 to 40% below model predictions. It was as if something in those layers was scrubbing them from the air. Consumption, Ilara breathed, staring at the vertical profile graph. The dips were sharp, layer-specific, like bites taken out of the atmosphere. Something is eating the cyanide, or catalyzing its breakdown, I cautioned. The old reflex of skepticism fighting a tide of dawning horror at that altitude. In minus 150 degrees Celsius haze particles. What catalyst is that selective, that efficient? She turned to us, her eyes alight with a terrible realization. We've been looking in the wrong place. We've been looking at the surface, at the lakes, but the atmosphere is the habitat, the haze particles. They're not just smog, they're microenvironments, protected, porous, with constant chemical feedstock raining down from above. If life exists on Titan, it doesn't live in the lakes, rains. It lives in the sky. The concept was staggering. Aerial biosphere, floating microscopic ecosystems, inhabiting the complex organic haze, consuming nitriles, perhaps using the weak UV light or even the static electricity from methane storms as an energy source, reproducing, dying, and snowing gently down to become part of the surface tar, a continuous, planet-wide cycle of life. And FOSSILIZATION. It fit. It explained the nitrile depletion. It explained the generic surface sludge, the graveyard of countless generations. It explained the silence of the surface. The real action was happening 100 kilometers up. But if that was true, why hadn't we seen it? Cassini's instruments had tasted the haze. The Inmes had sucked it in. We need to look at the Inmes spectra from the deepest atmospheric dives, Mira said, her fingers already flying. Not at the major peaks, at the noise, at the fragments. We worked for 72 hours straight, a sleepless, caffeine-fueled vigil. We focused on Cassini's final close flyby, T126, where it had dipped to within 1,000 kilometers of the surface, skimming the top of the troposphere. The enemy's data was a forest of peaks. We wrote algorithms to subtract the known dominant species, nitrogen, methane, benzene. What was left was a tangled undergrowth of thousands of minor spectral lines, most unidentified, Elora drawing on her knowledge of terrestrial microbial metabolism, created a search image for molecular patterns, ratios of carbon isotopes that might indicate biological fractionation. Oh, Dover-Avon carbon number preferences in hydrocarbon chains. Specific sulfur or phosphorus incorporations that had no abiotic reason to exist. The computer churned, comparing the spectral undergrowth against her biological template. The result was not a smoking gun. It was a haze of statistical maybes, a cluster of spectral lines around a mass of 250 atomic mass units that could be a fragment of a large cyclic nitrogen-containing compound. A slight but persistent enrichment of carbon-12 over carbon-13 in the acetylene family. A signature, often, but not exclusively, biological. A set of sulfur-bearing molecules in concentrations that made no photochemical sense. It was the same problem, magnified, compelling, frustrating, circumstantial. A whisper from the clouds. "It's not enough," Frank said, reviewing the summary. He looked exhausted. "It's another maybe. We have Enceladus screaming factory, Iapetus screaming colony, and Titan whispering maybe graveyard, maybe habitat. We need to resolve this. The mission clock is ticking." Cassini was in its final year. The grand finale, 22 daring plunges between Saturn and its rings, was already programmed. After that, a final, fatal dive into Saturn's atmosphere to ensure planetary protection. We had one last shot at Titan, flyby T-127, a distant pass, but with a unique geometry. The spacecraft would pass through Titan's magnetic shadow, the region where its atmosphere interacted with the plasma of Saturn's magnetosphere. It was a chance to see how Titan's chemistry affected the space around it. And we had an idea. The LURERE was Myra's idea, born of desperation and a deep understanding of Cassini's capabilities. The Radio and Plasma Wave Science Instrument, RPWS, she said. It listens to plasma waves, radio emissions. It's how we heard the lightning on Saturn. What if biological activity in the haze has an electrical signature? Not deliberate, but a byproduct. Cellular membranes have electrical potentials. Collective activity of billions of cells could, in theory, create a faint, non-thermal radio hum. It would be buried in noise, but if we know where and when to listen, it was a long shot, a Hail Mary. But it was the only shot we had. We got approval to program a special RPWS observation sequence for T-127 for 1 hour, centered on closest approach. The instrument would enter a high sensitivity mode, its receivers tuned to a specific quiet frequency band between 10 and 50 kilohertz, a window relatively free from natural planetary radio emissions. We were hunting for the faintest of hums. Propagules, spores. The Iapetus material is sessile, global. But how did it get there? Maybe it didn't evolve there. Maybe it was delivered. The idea was explosive. Panspermia within a single planetary system. Life we had to start using. The word not arising independently on 2 moons, but spreading from one to the other. Cassini has sampled the earring, Mira continued, her thoughts racing ahead. The earring is made of ice grains from Enceladus's plumes. It's a transport mechanism, spreading material throughout the inner Saturnian system. Iapetus is far out, but it passes through the diffuse outer reaches of that ring. What if, early in the solar system's history, Enceladus was more active? What if it seeded the entire system? It was a grand, terrifying narrative, and it made a dreadful kind of sense. Then Tethys, Dione, Rhea, I said. They'd be in the direct line of fire. Exactly, Myra said. We looked for anomalies like Enceladus. We should look for evidence of infection, of Iapetus-like staining, or of dormant. Whatever you call it, Frank made the decision. New priority. We scoured the data for every moon. We look for the pattern, the thermodynamic disequilibrium, the unexpected chemistry. We connect the dots. The pattern emerges. What followed was the most profound and frightening period of my scientific life, with the Iapetus data forcing us to think in biological terms, ecological terms. The Saturn system transformed before our eyes from a collection of geological objects into a biome. We started with Tethys. It had Ithaca, Chasma, a giant crack, We found nothing alive there. But the composition data from its trailing hemisphere showed an inexplicable enrichment in phosphorus, an element critical to genetics and energy transfer, not uniformly, but in streaks that matched the pattern of earring particle bombardment, as if the moon had been dusted with a fertilizer. Dione was next. We'd seen faint, wispy lines ice cliffs, but a reanalysis of magnetic field data from a 2010 flyby revealed a tiny, localized induction signature, a conductive layer under the ice, not global, like an ocean, a lens of salty, ammonia-rich water trapped under the southern hemisphere. And Cassini's plasma spectrometer had detected a faint, steady trickle of potassium ions leaking. From that same region, potassium regulation is a hallmark of cellular activity. MIMAS, the smallest, a dead ball of ice with a giant impact crater that made it look like the Death Star. Surely, here we would find nothing. But its orbit was the closest to Saturn, subject to the fiercest tidal stress. Our models had always said its interior should be warm, maybe even have a liquid layer. The data was ambiguous until we looked at the libration, the way Mimas wobbled on its axis. The libration was too large for a homogeneous, solid body. It implied an interior that was sloppy, not neatly layered, but heterogeneous, clumpy, as if its inner ice was not pristine, but mixed with pockets of denser, warmer, perhaps organically laced material, like Swiss cheese or a sponge. Rhea, the second largest, was the final piece. Rhea was old, heavily cratered, inert. It had a tenuous oxygen atmosphere from radiation, splitting water, ice. But Mira, digging into the most boring dataset of all, the catalog of micro-impacts on Cassini's dust shield, found a pattern. The flux of dust particles around Rhea was slightly higher than models predicted, and their composition, when she could get a spectral glimpse, was not just water ice. They had a faint carbon signature. Rhea was surrounded by a faint, dusty halo of organic material, not from geysers, from sputtering, as if its ancient, irradiated surface was slowly being eroded. And what was coming off was not pure ice, but a carbon-enriched rind, a skin being shed. One by one, the dots connected. Not one, but 6 moons showed signs of complex carbon chemistry, thermodynamic disequilibrium, and activity that defied simple geology. Enceladus, the active factory, the producer, Iapetus, the ancient, spreading biomass, the consumer, Tethys, fertilized by the earring Dione, harboring a possible, isolated, aquatic habitat, MIMAS, a potentially biotically modified interior, Rhea, exhaling a carbon-rich haze. We presented the interconnected findings to the director and a select few from NASA headquarters in a locked, windowless room. The graphs, the spectra, the thermal maps, the magnetic anomalies were laid out like evidence in a trial. We didn't claim discovery of life. We presented a system-wide syndrome, the Saturnian complex. The reaction was not joy nor wonder. It was a profound bureaucratic dread. The director, a brilliant physicist, leaned back in his chair, his face ashen. "You are telling me," he said slowly, "that the Saturn system is not sterile, that it is, in all likelihood, occupied by a non-terrestrial biology that exists in multiple, interconnected niches, that this biology manifests as everything from active geysers to continental-scale stains, to subsurface aquifers, to atmospheric dust." "Yes, sir," Frank said, and that the transport mechanism between these niches is the Iringa River of ice particles flowing out from Enceladus, carrying what spores? Chemical templates, living cells. That is the leading hypothesis, Alara said. The director steepled his fingers. The implications for planetary protection are apocalyptic. Any future mission to land on, say, Enceladus or Titan, becomes a Category V planetary protection nightmare. We could contaminate it with Earth life, or worse, bring something back. The public reaction, the theological, philosophical upheaval. We can't hide this, I said, surprising myself with my own vehemence. This is the single greatest discovery in human history. It changes everything. It changes nothing, the director countered. If we cannot prove it conclusively to the satisfaction of science and the public. Right now, you have a web of circumstantial evidence, so compelling it's terrifying, but it is still circumstantial. We need direct observation. We need microscopy. We need to see a structure. He was right. The thermodynamic and chemical signatures were like seeing the heat and exhaust from a hidden factory. We needed to see the assembly line. Cassini can't do that, the director continued. It wasn't designed to. Its mission is ending. We have the grand finale orbits planned, then impact with Saturn to protect the moons. That plan must not change. We cannot risk Cassini, laden with Earth microbes, crashing into Enceladus or Iapetus. Saturn's atmosphere is the only safe graveyard. He stood up, pacing. Here is what we will do. You will prepare a comprehensive internal report on the Saturnian complex. It will be classified. We will use it to design the next mission. A mission with one goal: to land at Damascus Sulcus, drill through the ice, and look into that vent with a microscope, or to scoop up the dark material of Iapetus and sequence its whatever it has. That mission is now the top priority for the next 2 decades. But until it flies, the public story remains. Enceladus is a promising abode for prebiotic chemistry. Iapetus has a mysterious dark coating, full stop. We were being told to sit on the truth, to become curators of the greatest secret ever kept. It felt like a betrayal of science, and the only rational choice. As we left that meeting, walking back to the vault under the fluorescent lights, Myra spoke what we all felt. It's not just a secret we're keeping, she said. It's a timeline. We've found the fire. Now we have to decide whether to shout a warning or to spend 20 years building a fireproof suit before we get any closer. We entered the vault. On the main screen, a real-time simulation of the Saturn system spun silently. The moons traced their elegant arcs. It looked so peaceful, so clean. I knew now it was not clean. It was humming with a slow, cold, alien vitality. We had mapped the outlines of a shadow biosphere. We had heard its breath on Enceladus and felt its chill on Iapetus. But in our quest to understand the machine, we had stumbled into a darker, more fundamental mystery. We had found the what and the where. Titan loomed in our minds, a glaring, unanswered question in our emerging map of the Saturnian complex. It was the giant, the anomaly, the elephant in the room of astrobiology. Larger than Mercury, shrouded in a smoggy atmosphere, denser than Earth's, carved by rivers and dotted with lakes of liquid methane and ethane. If Enceladus was a hidden geyser-fed hot spring, and Iapetus a sun-kneading lichen crust, then Titan was a whole alien planety cryogenic parallel to Earth with its own hydrological cycle. It was the obvious place for life, the most habitable world in the outer solar system. And according to every instrument we had, it was dead. Our covert mandate now included Titan. Frank secured reprocessing priority for all Titan flyby data under the vague guise of atmospheric chemistry synthesis for future mission planning. It was a thin cover, but it gave us access. We started with the basics, re-examining the great discoveries of the Huygens probe and Cassini's radar. The rounded, icy pebbles at the Huygens landing site in the Shangri-La Dune Sea Vidance of fluvial transport, the vast, dark Ligeia Mare and Kraken Mare, so still their surfaces were mirrors, reflecting not a ripple. The dendritic river channels, carving through the water-ice bedrock. The evidence was for a world in geologic motion, driven by methane, not water.